Welcome to the Neural Implant Podcast, where we talk with the people behind the current events and breakthroughs in brain implants in an understandable way, helping bring together various fields involved in neuroprosthetics. Here is your host, Ladan.
Hello, everyone, and welcome to the Neural Implant Podcast. Today's guest is Gordon Wilson, and he is the CEO and founder of Rain Neuromorphics. It's basically a neuromorphic computer chip which simulates the brain a little bit more than like CPUs and GPUs. And what this does is it allows the computation to be much, much more efficient. So he was talking about, it's like hundreds of times faster and uses hundreds of times less energy on top of that. So really for the kind of stuff that we as neuroscientists and neural engineers we need to do, it's very useful because potentially you could have thousands of times less energy draw than what you would normally have for like spike sorting and stuff like this. So really cool stuff. Actually, it's kind of funny. We had been in contact for, I think, almost 2 years now. And he is a alumni of University of Florida, which of course is where I'm at right now. This is the roots. This is kind of where it all started. Well, Gainesville is kind of a hub for a lot of things. It's pretty crazy. Small world. But anyways, I thought this was really interesting. I mean, again, some of these episodes aren't exactly brain-computer interfaces, but this technology could very much facilitate brain-computer interfaces, really reduce the data transfer that's required in order to make these things work by a lot, by like 3 orders of magnitude. So really cool stuff. Hopefully you learned something new from this. Enjoy. Gordon Wilson, pleasure to have you on the show. You are the founder of Rain Neuromorphics, which is a brain-inspired processor for artificial intelligence. So basically changing the way that the actual substrate or the way that the computer is designed to more mimic AI and to better run like AI algorithms, deep learning, and this has very good implications for the brain as well. And I thought a really funny quote that you had said was, to understand the brain, you need to build one. Do you want to talk about this a little bit?
Yeah, absolutely. And sure, yes, I'm the CEO and co-founder. I share the co-founder title with 2 other folks, Jack Kendall and Juan Nino. Juan, who is actually a professor at the University of Florida over in your neck of the woods in Gainesville. But yeah, we're doing some really radical stuff at Rain Neuromorphics. And I love that quote that you just mentioned, to understand the brain, you need to build one. This is something that we put on the back of our t-shirts, actually. I believe it's a Feynman quote. It's that which I cannot create or that which I cannot build, I cannot understand. And I think it really points to the intellectual crux of so much of what we do, in both in terms of how we're inspired in what we're building, but also the ultimate consequences of the hardware that we are developing. On one hand, we're building hardware with a direct commercial application, and that's to make AI more scalable so we can build bigger neural networks, which are smarter neural networks and can solve harder problems, and also making that scalability very efficient so we can save energy, because today's neural networks, the biggest and most capable ones, take on the order of kilowatts to run, and they need to be put in dedicated data centers. We're trying to build hardware that will allow this to be an autonomous robotic brain that can sit inside of a device. But on the way to doing that, we are taking all of these clues from the brain and everything from what are the sparsity patterns that allow the brain to scale up to its extraordinarily vast number of neurons and synapses, or how can the brain perform global optimization when it's only really has information for local optimization. There are so many pieces of understanding the brain that I think by building brain-like hardware that we can ultimately hark back and apply to our understanding of neuroscience. And so much of what we do is really about directly enabling new applications, but it's also about, I think, uncovering the secrets of the brain by building something that is more brain-like than ever before.
That's crazy. Okay, how do you do that? I mean, like, computers have transistors and everything like this. How do you keep the transistors and just kind of organize it in a different way? Or what's the actual, I guess, secret sauce behind all this?
Yeah, so there are quite a few different things that we're doing, but I think one of the most fundamental ones to understand is this difference between digital signal processing and analog signal processing. In particular, all the computers that we have been using over the course of our modern computing history have been built on something called the von Neumann architecture. So there was this really, really brilliant computer scientist, engineer, John von Neumann, who conceived of this computing architecture, which has become the norm. And basically, all that this really means is you have a processor on one side and you have a memory on the other side, and you have a bus that moves information back and forth between the processor where you do calculations and the memory where you store information. And all of our computers, all your laptops, all of our smartphones, these have all been built with this von Neumann architecture and with this separation of memory and processing. Now, for artificial neural networks, the type of math that we use to build all the deep learning neural networks that have shown all this amazing progress for things like vision and speech and natural language, we've had to run them on these digital hardware. And the reason why GPUs became the de facto winner is because they had many little cores, many little processors, so lots of processors that were distributed across, so they could do lots of little pieces of math at the same time, because the kind of math that's underneath these neural networks, it's called matrix algebra, and it's lots of little pieces of addition and multiplication. So GPUs were naturally the ones that could do this math really well, and that's why they are the standard hardware today for neural networks. They can have many operations at the same time, but they still have this separation between memory and processing. They're still von Neumann machines. Now, if we take a step back and look at the brain, in biology, we don't have any separation of memory and processing. Memory and processing happens in the same functional unit, in the synapse. So the synapse has a memory of the signals that pass through that, and that is sort of the strength of that synaptic connection. And then when you send a signal through the synapse, it can be, upregulated or downregulated. And so it's used as a processing unit as well, as it's then accumulated into the next neuron. So one of the key intuitions behind our hardware is that we are moving away from von Neumann. We're not using digital processors to do this matrix math, but we're using analog processors to do this matrix math. And this is called processing in memory. And we're not the first people to do this or to conceive of this, but basically there is this other type of chip that you can use to do these matrix operations. And instead of doing the math in dedicated digital logic, you actually do this math by exploiting physics. So you basically have inputs and outputs. The inputs can send in voltages, the outputs read out currents, and then you have a big grid. These are the conventional chips that have been made for this that have resistances. And these resistances can be adjusted. Those become the weights of the neural network. And when you release a vector of voltages, Ohm's law happens. So a voltage times a resistance equals a current. And you can perform that matrix math just by using physics. It's really, really elegant, a way to do that. So this is a natural advantage of analog computation, that it can actually be very fast and very energy efficient when you do it this way. What made our core technology different, and what was our key innovation that was started some 7 years ago that became the foundation of our company, was a reimagination of that analog multiplication architecture. Basically, every chip that had been made before had inputs and outputs on the edges of a chip. So the main real estate of the chip was consumed by this big grid of the synaptic weights, the resistances. What our technology does is it moves that memory layer from inside the chip to on top of the chip. So we now have this, it looks pretty wild. It's a random mesh of nano-wires that we place on top of a chip, and that means we can fill the entire chip itself edge to edge with inputs and outputs. So as opposed to just having inputs and outputs on the edges of the chip, we now have a chip that is filled with inputs and outputs, has much better scaling, but still retains these advantages of analog processing. It's called the memristor nano-wire neural network, and the immediate benefit is it allows you to scale up this matrix multiplication to sizes that are just way, way, way bigger than you could do with digital or analog approaches. And that matrix multiplication size directly corresponds to the size of a layer in a neural network. So that means with our hardware, we will be able to build bigger neural network layers than ever before. That's the crux of kind of our core technology, right? Scaling up analog so we can build bigger neural networks.
That's incredible. Yeah, that sounds really cool. I mean, that's definitely the future. So I know that between the CPU and the GPU, I mean, I looked this up one time, and like you said, the GPU can do very simple, math. Like there's only like 8 or 11 combinations or 8, 11 functions that it can do or whatever. And so everything has to be optimized for the GPU. But if you can do that, the GPU is 800 times faster than the CPU. And that number might be different. I don't know if it changes year to year or what. How much more powerful is your guys' stuff compared to a GPU or a CPU?
Yeah, that's a great question. And you're absolutely right. GPUs are naturally suited to do this math far better than CPUs. The main reason is just because they have many more cores and they can do a lot more math at the same time. A CPU is handling more complex math. A GPU is handling simpler math, but a lot more of it at the same time. So if you compare our hardware to a GPU, we've done math to compare it to a V100. So that's the Volta, which is currently the primary GPU used in data centers. We're looking at comparing that matrix multiplication operation about 150 times faster compared to a V100 for this very large matrix, while still cutting power consumption by about 50x. So we're looking at some pretty striking numbers that we can achieve compared to a GPU because we have an architecture that can exploit these fundamental advantages of analog.
Wow, that's incredible. That's pretty cool. I mean, that'll, I think, unlock some doors for this. So what's your guys' progress on this? Have you actually built this? Does it use traditional semiconductor facilities to be able to build this? Or is this some kind of like novel unobtainium kind of material to be able to build this?
Yeah, so we have built chips so far, and we have done an extensive amount of work in development of our nano-wires. But you can kind of conceive of our chip as consisting of a conventional piece and an unconventional piece. So the conventional piece is standard kind of chip stuff. Standard, what they call CMOS, which is complementary metal oxide semiconductor. But basically, everything that's underneath the nanowires. So these are the digital analog converters that send information in, convert them into analog signal, analog digital converters that will take information out and send it out of the chip. They have some pretty simple analog circuitry. And then you have the unconventional part, which are these nanowires. And these nanowires are placed on top in a kind of stochastic fashion. And this is something that we've had to develop ourselves. We started doing this work at the University of Florida in the laboratory of Dr. Juan Nino, one of our co-founders. But since we moved to California, we've done a huge amount of work on the kind of nanoscale wires at a laboratory at Stanford. So we've been able to fabricate these wires, perform matrix multiplication through them. And it is a little bit of a special recipe that we use, but what I can say is we are using something called the memristor, right? So the memristor is a portmanteau, a word that combines memory and resistor. It's basically a family of devices that have tunable resistance and that you can use as a resistor, but adjust that resistance. And this makes it into the ideal artificial synapse. So there's a range of materials that you can use for that. I won't be able to say exactly what we're using, but we are essentially putting the memristors in the wires themselves and allows us to pack a whole lot more of them also into the same amount of space than you'd have otherwise.
Okay. So basically, more or less traditional standard semiconductor devices. And then on top of that is your special sauce of the nanowires. Very cool. Okay. So how does this affect the neural implant community? I mean, what could this potentially be used for in brain-computer interfaces?
Yeah, that's a great question. So one of the challenges with building brain implants and brain-computer interfaces is creating the kind of interconnect between a slow analog, massively parallel system and a fast digital, more serial system. I think that the company Paradromics really does articulate this problem really well. I'm sure you've spoken with Matt Engel, who's a really nice, really brilliant guy. And they're solving this problem one way. But when we think about brain implants, we want to have the type of really low power, high dimensional signal processing that can be embedded. We need chips that can handle, again, these really high dimensional matrix mathematics problems, but still be very energy efficient. And you're never going to put a GPU in someone's brain. It's just way too much power. You're not going to put a 200, 300 watt thing onto someone's brain. Maybe you can, but it'll be like a big helmet. And it'll probably be pretty unwieldy and be pretty difficult to integrate. But I think that chips like ours that are analog, but also scalable to support this really high dimensional math will be far more suited to having kind of on-device in-brain processing. They may not do all the processing, but they will certainly be able to do some of the pre-processing so that the information that you transmit from that implant to somewhere else will be much more condensed and more efficient. Because that's a huge problem that people are facing with any type of, I think, AI system or embedded system. Like, how can we process information at the source such that we don't have to transmit all of that raw information in these massive packets that are slow, low latency, and expensive?
Yeah, I mean, we did have Matt Engel on the show, and he was talking about basically the amount of data that they have to throughput with tens of thousands of electrodes, and it's the equivalent of many hundreds of Netflix streams at the same time. And they had this device that was basically the size of like a Coke can, just to cool it down and process everything. And so, obviously, if you can get down that energy consumption and thereby heat consumption,
it was 150x faster, 50x less energy, but those are still, we believe those numbers can be improved upon massively. So those numbers are from a circuit architecture that we have built out. You're looking at about, 3 orders of magnitude, 3 to 4 orders of magnitude there.
That's crazy. That'll enable this technology, I guess. That's really cool. So, okay, is this programmable? I mean, can you go in there almost like Arduino or something like this and change things up? Or is it baked into the way you build it?
Yeah, so it's not, so on a fundamental level, yes, I should say. So the benefit and the goal of the memristor is that it is a programmable resistor. So as opposed to being hardware that it's like flash memory, where you have to send a massive amount of current into that flash transistor to change the resistance, these are programmable in the sense that you can move the resistance values around, you can adjust the synaptic connections with very little energy. In that sense, yes, it's programmable. In the sense of it being as easy to use and intuitive as, say, an Arduino or a Raspberry Pi, we're not there yet. But the ultimate goal is to have a developer ecosystem where people can explore and program these things below just the Python interface layer that we're building for them. But no, I think that on a fundamental level, when you think about programmable, it's like, can this support different models? Can this solve different types of problems? And that's absolutely. And that's because of the programmability of the memristor of the device that we're using.
Wow. That's really incredible. I really hope this goes through. So I want to talk a little bit about your journey as a founder. I mean, you started here in the land of paradise, Gainesville, Florida, and University of Florida, and then you moved over to a very expensive Silicon Valley. You did Y Combinator, which is pretty cool. That's like one of the premier incubators startup incubators over there. How was that, and how have things been basically getting this company off the ground?
Yeah, well, Y Combinator was a fantastic experience, and I would recommend it to anyone who has the opportunity to go. Obviously, it's competitive, so if you can get in and make that possible. Y Combinator was really great for us because it did provide us with a big network and kind of a landing strip to the Bay Area. We actually had made the decision to move to the Bay Area independent of doing Y Combinator. We were planning to relocate as we had closed our first very large round of seed funding the February before that summer that we did YC. But it's been a massive relocation and a big adjustment to move to the Bay Area. Originally, we were really debating about staying in Gainesville because we felt that we would have kind of a lock on talent that was graduating from UF. All three of us, the co-founders, had deep affiliations with UF, having been students or a professor. And the money went a lot further in Gainesville than it went here in the Bay Area. But when that first year that I was working with Jack and Juan, I found myself flying out here maybe once a month, and it became almost half of my time because everyone that we wanted to talk to, whether it was our customers, our potential research partners like OpenAI, or our investors, prospective investors, everyone seemed to be here in the Bay Area. And then we kind of doubled down and thought about talent and the team we want to build. And we're doing an extraordinarily multidisciplinary project here where we have expertise in materials science and device physics, to expertise in kind of the cutting edge of deep learning algorithms and also circuit design. And there was some of this in Gainesville, but we could find the world's best talent here. And happily, when we moved here and relocated here, we have brought on some really, really, really talented folks, some really humbling folks to our team who have been able to really step our company up in terms of our productivity and our credibility, because we still have a long road ahead of us and a lot more capital that we'll need to raise in order to fully commercialize our technology. But being able to recruit the types of folks we found here and find the continuous sources of capital have, in my mind, made it worthwhile.
Yeah, that's really cool. I don't know. I mean, I guess I'm too maybe financially sensitive or cheap or whatever to basically be paying double or triple to have access to that kind of stuff. But at a certain point, I think that would make more sense. Kind of what you were saying is like spending, half your time over there, then be like, well, it actually makes sense for me to be over here. And then you guys looked like you raised some money August of 2018. And so you don't have a product, you're just still kind of developing stuff. And then eventually you'll be able to sell something, or what's kind of the market plan to be able to make money?
Yeah, so we are definitely still an R&D company fundamentally right now. We are not shipping hardware as of today, I should say. And we still have several years before we'll be manufacturing that hardware at scale and shipping that to customers. But that said, for what we are developing right now, we have a vision of neural networks and the way neural networks will look in 3 to 5 years and beyond that is pretty different from the way neural networks look now. And we are releasing some products that are essentially software products that will help data scientists explore some of these characteristics that we are very bullish about, kind of the way neural networks will evolve. So one of which is today's artificial neural networks are deep. They have many layers, but they are dense. So these layers are very densely connected. They're mostly fully connected from one layer of neurons to the next. This is not like the brain. It does have many layers, but it's much wider. Those layers have many more neurons in them, and they're not fully connected. They're sparsely connected. So our hardware that we're ultimately bringing to market will be a massive, sparsely connected array of neurons. So we have software libraries that we're going to be releasing this summer that will enable data scientists to explore sparsity in simulation first, and kind of start to ask some really interesting questions about what happens when we build our artificial neural networks in this sparse regime. There are some incredible results that are starting to come out. Everything from sparseness allows for scale, which is almost an obvious conclusion, but also when you're only activating a small amount of neurons at any given time, you can create a really, really robust system to external noise. This is something that is this type of noise and sensitivity has really plagued reinforcement learning and generative models. And so anyway, we want to release these types of products and enable people to explore in a software level kind of how this will change the architecture and performance of neural networks in the future.
Wow, that's pretty incredible. And then you were talking about a 3 to 5 year timeline for this?
That's right. So ideally, we want to get there in about 3 years. For us, the biggest variables will be essentially tweaking the performance of these nanowires. We're looking to go to market with our first product at about 2023 in terms of shipping that hardware itself.
Wow, that's really cool. I mean, you guys have only been around since June 2017, so you guys are really fast, I think, with this.
Well, there's a need for this kind of hardware. And there's out here in Silicon Valley, people are talking about it as if it's the word they love to use is a Cambrian explosion in silicon. There has been, I think in the last 2 years, some $3 billion that's been invested in next generation silicon just for AI. And this is because it's just the compute costs are so obvious to anyone who takes a look at it. There are all these neural network models that are really promising. Like the most exciting ones from the last year are natural language understanding, neural networks that could read essays and write essays and come up with language on their own. These are really cool. We want to apply these. We want to give these capabilities to all types of companies and enable them to automate the work that humans have typically done in terms of text analysis. But these things are so damn expensive that you can't deploy them. And I think that's a big reason why we're trying to move quickly, in addition to observing many other folks, who are trying to solve similar problems.
Yeah, definitely. The data centers, I mean, that's huge. And then there's also potential, like electricity and the power is one of the main costs in this. Actually, is there a way this could be used for cryptocurrency mining?
So With our nanowire interconnect, we can't explicitly do hashing, but it is something we've looked at. And there are other types of kind of security adjacent applications that are pretty interesting for us in terms of, one thing that's pretty darn cool is that when you deposit these wires in a stochastic fashion, you create something called a puff, or a physically unclonable function, because of just the sheer combinatorial variety of how many ways you can deposit those wires. So that is something that is pretty interesting from a security perspective. We've been curious about crypto, but we're most excited about the neural network applications here.
Yeah, for sure. Yeah, and I guess, you were talking about there's a gap. Looking into this, investors are investing a lot of money into this because I guess there's like a computing gap. We're kind of thinking, okay, Moore's law is running out of steam at some point. We're going to have to figure something else out because we're literally at the limits of physics. So this is your thesis, is that this is the way forward in terms of computation and cost of computation, right?
Exactly. Yeah. No. So you see NVIDIA with their GPUs and many other companies are all on this kind of von Neumann track, right? And this requires them to scale with Moore's law. This requires them to basically figure out all the ways that they can fit more processing cores into one chip, to how they can break memory into a lot of different pieces so they can localize that memory access. But they're all kind of following the same playbook. And at the end of it all, Moore's law will not sustain forever. And the costs for us to get down to 5 nanometer, 3 nanometer, 2 nanometer technologies will be immense. So we need to kind of reset the scaling clock in some way. And we really do believe that moving to analog and moving to kind of a 2.5D architecture that allows you to reset that and start at a much larger geometry. For example, our first chip that we taped out is on 180 nanometer, right? And the one that we have compared the stats to, the 150 and 50X, that's on 65 nanometer technology. So comparing a 65 nanometer process node to a 17 nanometer process node, we're still getting that performance gain. So yeah, that we think we're going to do it.
That's crazy. That's fascinating stuff. I absolutely love this. I'm going to be following your guys' work. I think this is really cool. Gordon, is there anything that we didn't talk about that you wanted to mention?
No, I think we covered most of it. I mean, if there's anything that I want listeners to really remember and take away, it's that artificial neural networks today are really capable and really exciting, but they are still tiny when you compare them to the brain. The biggest neural networks today are a few million neurons and maybe 10 billion synapses. Our brain is 86 billion neurons and nearly half a quadrillion synapses. And the limit to the advantage of scale, we have not reached it. There is no end in sight. That just building bigger neural networks seem to beget better and better results, smarter systems. So if there's one thing that I want people to remember, it's that scale matters. And whichever way we can find to scale, we won't build a von Neumann brain that is as efficient as the human brain. So hopefully we can think about other ways to do it, like what we're doing.
Yeah, love it. Thank you so much.
Awesome. Thanks so much, Ladan.
Hope you enjoyed the show and were able to learn something new, bringing together different fields in novel ways. Until next time on the Neural Implant Podcast.